Thanks, Don. Well, I'm going to have to apologize here because I got really fancy and I threw Gwen Ellen a real curve. So I don't know how this is going to turn out. Greatest story ever told. That's my sweetie Zaw. She's out there someplace and she asked me, isn't it a bit presumptuous of you to say you're telling the greatest story ever told? Let me answer that by telling you a story. In Boston, Massachusetts, there is a small graveyard between two storefronts right downtown. Happens to be the same place where Paul Revere is interned. And there is a stone there labeled Martha Goose. And she is reputed by some to be the Mother Goose who told all those wonderful stories. She didn't popularize those stories, though. Her son-in-law wrote them, attributed it to Mother Goose. So all these wonderful stories I'm going to tell you today, you can call me the son-in-law. And like all stories, this starts in the beginning. Every culture has their own Genesis story. And they're all fairly similar. You can run them together. Let's start with the tribes of Galilee. In the beginning, God created the world, and the world was in darkness. And God said, let there be light. And he created the world, divided the world into light and darkness, and he said it was good. Switching on to the Basonga people who live in Central Africa. Their story goes on, but the great god Boomba had a stomachache. So he vomited up the plants and the trees, but his stomach still hurt. So he vomited up the animals. Switching over to the Mayans, but the maker was sad, for there was no one to worship him. So he made the mud people. But the mud people were dull, so he allowed the rain to wash them away, and he made the stick people. But the stick people spoke only gibberish. So he was going to destroy them, but they escaped into the forest and became monkeys. But then he invented the humans, and the humans worshipped him, and he was happy. Finishing on the story, according to the Navajos, so first man and first woman ascended to the surface through hollow reeds, and there they met and decided to live together. Now, what do all these stories tell us? They tell us that as far back as we can go in the written word, or as far back as oral tradition can tell us, our kind has been wondering the big questions and trying to answer them. Why are we here? Who are we? Why is there a here? And it wasn't just the ancients with their limited knowledge who asked these questions. One of the brightest people in our generation with a tremendous education asked, why does the universe go to the trouble of existing? Or you take a great storyteller like Douglas Adams, wrote a whole book dedicated to what is the answer to life, the universe, and everything. So when we get through here today, we'll have enough knowledge that I'm going to tell you the answer to life, the universe, and everything, according to Douglas Adams. I'm going to tell you why the universe goes to the trouble of existing, according to Stephen Hawking. And I'm going to tell you my version of the meaning of life. One little helpful hint, we're going to be dealing with a great deal of time, billions of years, so it might help you to know a principle of time. Time flies like an arrow, fruit flies like a banana. Okay. Cosmologically, the greatest story ever told doesn't begin with a great storyteller. It was written for us to read and to decipher if we're smart enough. Where was it written? In the rocks. The rocks under our feet. The rocks that rain down on us from outer space. The rocks the astronauts brought back from the moon. The rocks our intrepid robots are out there analyzing for us just now. And it's written in the photons that stream down on us from the far reaches of the universe. And it's written in our very DNA. So who wrote this great story? I will tell you. This story was written by the great goddess physics. And the great goddess physics begot chemistry. And chemistry and physics begot geology. And geology and chemistry begot life. And they all collaborated to write the greatest story. And here's what we know of that story so far. And a little bit of how we know it. Disclaimer, we have some billions of years to cover an entire universe. Some details may be omitted. So hang on to your seats, because here we go. In the beginning. In the beginning, matter and space and time all came into being. Before the first instant of the universe, none of those things, nothing existed, not matter, space, or time. And they all came into being in what we call the Big Bang, and this is the artist's conception, but in reality it probably looked more like that. So how did this happen? That is a very good question. Normally when somebody says, that is a good question, that means I don't know. In this case, it means nobody knows. But, went off the screen there. Sorry about that, Joanne. But, just this year, a group working for NASA who were trying to develop and drive for an interstellar spaceship came up with what they thought was a micro mini Big Bang. So, we're not through reading this story yet. Stay tuned. So, the evolution of the universe. We may be a little fuzzy on how it began, but we have the evolution down pretty well. At the very beginning, everything was compact and everything was together, and it began to separate out. 1 second into the universe, the elementary particles, quarks, electrons, photons, and neutrinos had separated. Let's do a real quick run through of what those things are. Quarks are the things that make up protons and neutrons. We all studied on those in school. They were predicted in 1964 and discovered only 4 years later. Protons and neutrons had been discovered in 1911 and 1932, respectively. The electrons, those are the little guys that whiz around the atomic nucleus to make it into an atom. They were detected as early as 1897. By the way, this story, that's about the oldest date we go back. Most of what I'm going to tell you today, virtually all of it, was discovered in the last 125 years, most of it in our lifetimes. So let's get into photons and neutrinos. Photons are nothing more than particles of light. Yes, light is a particle, but also a wavelength. This is really hard to get your mind around. We're used to the part in the middle there. That's when we can see the colors of the rainbow. But there are different spectrums that are the same property, just different wavelengths. We get into the ultraviolet, which we can't see, but which causes sunburn. X-ray, which is very useful, you know, because it can penetrate. Gamma rays, which are much more powerful and would be a real problem for life on Earth, except we're protected from them by our atmosphere. Going the other way, there's infrared, which we can't see but feel as heat. Incidentally, some insects can see in the infrared. Get into the microwave, which you use for our ovens and radars, and you may remember that the early microwave ovens were called radar ranges, and of course the radio waves. All the same, just one electromagnetic spectrum comes through in particles. And neutrinos. These were called the ghost particles. They are so light and so elusive, they were thought to have no weight at all for a long time, no mass at all. And they are so completely unreactive that they can travel through the entire Earth. Most of them do. It makes them devilishly difficult to detect. There are billions of them going through your body right at the moment. You're completely unaware of it. These were theorized, that is predicted in 1930, but only in a third the amount predicted. So something was wrong with the theory or something was wrong with the detector. Took another 35 years to discover there are 3 different kinds of neutrons. Problem solved, starting to give me a really good feeling for the smart guys that make these predictions. That's okay. So, what we were saying there is 1 second after the beginning of the universe, we had these elementary particles, and the universe was incredibly hot. So what's incredibly? We'll get into that in a minute. At this time, the universe keeps expanding, and it's cooling. And at some point, it gets cool enough that the forces separate out. Gravity, which ancient man thought he understood gravity, and then we thought we understood it better after Sir Isaac Newton, and now we think we really understand it after Einstein, and are some of the smart guys out there thinking, wait a minute, maybe there's a little more to gravity. We don't know yet. There's a strong force. That's what holds the nucleus together. And the weak force, it's repulsive instead of retractive, and that's what causes radiation if something gets out of the, the nucleus, causes the radioactive particles. And, where was I? Oh yeah, electromagnetism thought to be 2 different forces until electromagnets were discovered. So, when the universe had cooled down to 10 to the 32 degrees Kelvin, the quarks combined to form protons and neutrons. What's 10 to the 32 Kelvin? Kelvin is absolute temperature, absolute 0 in Kelvin. That's as cold as you can get. No heat. That is 273, minus 273 Celsius. So 10 degrees Kelvin, super cold. 100 degrees Kelvin, still really cold. 1,000 degrees Kelvin, that'll melt glass. 10,000, that's hotter than the surface of the sun. That's 10 to the 4. We're talking 10 to the 32. That cooled down from incredibly. That gives you some idea of how hot incredibly was. But then the whole universe was that big when we started. So at that point, the quarks and the neutrons the quarks combined to form protons and neutrons. Now, the universe is 3 minutes old. I'm going to have to really hurry. We've got 10 billion years to go. The temperature was 10 to the 9. That's 1 billion degrees Kelvin. At that point, the protons and the neutrons combined to form the nuclei of the 3 lightest elements, hydrogen and its isotopes, helium, and a little bit of lithium. By the way, the theoretical boys not only predicted that this was going to happen, but they said it would be 75% hydrogen, 25% helium, some tiny fraction of a percent lithium, and when the astronomers got so they could measure it, that's exactly what they found. I stand in awe of these guys with the big brains. And that's all that happened for about 380,000 years, except the universe is growing bigger and colder. And at that point, the temperature is about 3,000 degrees Kelvin. And the electrons and the electrons go into orbit, atoms are formed, and the dark ages began, the cosmic dark ages. What does that mean? The cosmic dark ages, up to this point, all those photons we were talking about are bouncing off all these little particles, like so many pinballs in a pinball machine. Had there been anybody there to observe it, it would have looked like a great fog. And all of a sudden, the atoms formed, those photons are free and they're flying through space. This is as far back as we can see, back to within 380,000 years of the beginning. So how do we know that this is true? Well, Albert Einstein, a German, in 1915 gave us a special theory of relativity, which when you press it to its limits, it kind of predicts that the universe is going to be this way. A Russian, Friedman, in 1922, carried Einstein's work a little further and came up with the notion that the universe could not be static. Lemaitre, in 1927, Belgium, carried the work even further and said the universe had to be expanding. And in 1929, Edwin Hubble, using the state-of-the-art greatest scientific instrument, the 200-inch Hale telescope on Mount Palomar, discovered that the little bitty smudges that everybody called nuclei that the astronomers were seeing were really more island galaxies. You see, at that time, we thought the whole universe consisted of our island universe, what we now call the Milky Way. And he discovered there were other island universes out there. We call them galaxies now. He further discovered by redshift, which we don't have to get into right now, that they're flying away from us, and that the ones that are receding the fastest are the furthest away. Edwin Hubble realized that this was of paramount importance, and he actually campaigned to win a Nobel Prize, which he was denied because Nobel hadn't given a prize for astronomy. But you can see that if everything is receding from us and the further ones away are receding the faster, you calculate this backwards, run the universe backwards, which you can do. A theoretical model, calculate it. You could calculate its age. And Hubble was the first guy that tried to do this, but he didn't have enough data, and the answer he came up with was woefully short. The geologist said, well, that can't be because the Earth is older than that. But time, instruments got better, more data was accumulated, and by the 1990s, we knew that the age of the universe was somewhere between 10 and 18 billion years. The geologists were okay with that one. But it gave another problem. There's some other people came up with a different idea called the steady state theory. That means steady state theory says that the universe has always looked pretty much like it looked now. Sure, it's expanding, matter forms to fill in the voids, and so it's always looked the same, and it will look the same in the future. Big Bang, of course, was that the universe began at some period of time and has evolved into the state we now know it. Incidentally enough, the term Big Bang was thought up by the steady state folks to heap scorn on the Big Bang people, and they adopted it. As time went on and the observations got better, we could see galaxies further away, which meant we were seeing them as they were a long time ago. So we were seeing them in previous periods, and the galaxies were looking different. They were looking younger to the astronomers. So the the Big Bang folks were starting to win the day, but the steady state folks didn't give up. And then these folks showed up, Penzias and Wilson, and in 1965, using that instrument behind there, they discovered the cosmic microwave background. Now, the cosmic microwave background is nothing more than all those photons that were released when the universe was 380,000 years old. This pretty much proved that the steady state folks were wrong and that the Big Bang folks were right. A little bit of irony here. These guys weren't looking for the cosmic microwave background. They didn't know what it was when they found it. They didn't know what it meant. Somebody got them in touch with the theoretical boys in Princeton who figured out that it must be out there and that would prove the point, but they didn't have the money to build this instrument. The irony is, these guys won the Nobel Prize that eluded Hubble. And here's a picture of the cosmic microwave background, not taken by Penzias and Wilson, but by the Wilkinson Microwave Anisotropic Probe, which was launched in 2001. It was a satellite for the sole purpose of taking a picture of the cosmic microwave background. This was the final nail in the coffin of the steady state theory. And figure this is like a sphere. It's stretched out so you can see it there. The dark spots are where the universe is the coolest and least dense, and the brighter spots where it's more. They further were able to determine the temperature of the universe at this point, less than 3 degrees Kelvin, which matched very nicely with what the theoretical people said it should be. And by way that I have never been able to figure out, they calculated the age of the universe, which is 13,779,000,000 years. That's how long ago the Big Bang was. So, remember this. This is very important. Nothing in cosmology makes any sense without the Big Bang. Okay, so we started about the Dark Ages, and now nothing happens for about 1 billion years. Actually, first stars started showing up about 700 to 800 million years into the age of the universe. Gravity is magnified as taken the clumps, the denser clumps, pulled them further and further together. The stars start forming, and then the stars start lumping together into small galaxies, 1 billion years old. Let's take a little bit of time to pry into the life of stars, because that's what we're seeing here. And this is Neil deGrasse Tyson. He is a physicist and a popularizer of science. And when he was just a lad and first realized that he wanted to know something about the stars, he went to the library and he asked for a book on stars, and they gave him a book on Hollywood. But we will go that wasn't the stars he was interested in, nor is it us. Paradoxically, the larger the star, the shorter its life. It kind of reminded the old song, "They're gonna fuse fast, shine bright, die young, leave a beautiful legacy." Okay, so the life of a star is a balancing act between gravity and fusion. Gravity pulls it together tighter and tighter. In the center, it gets more compact, hotter. The nuclei of the hydrogen atoms are bouncing together so hard that they start fusing. This creates energy. The energy balances the gravity, and that's what happens for the entire lifetime of the star. But the bigger the star, the greater the gravity, so the faster it fuses. So we'll get into the legacy just a little later. Let's go through the size of a star, starting with the smallest one. Brown dwarfs, less than 1/10 solar mass. Solar mass is the mass of our sun. So the 1/10 solar mass is 1/10 life, and these are going to live forever because they aren't really stars. They're not big enough to start fusing. And we get into the dwarfs, 1/10 to 0.8 solar masses. These live from 100 billion to 10 trillion years. This means that every one of these that ever came into existence is still out there because the universe is not old enough for them to have burned down. Well, they're all out there except the ones who've had an unfortunate encounter with a black hole. Then we get into the stars, our range, solar range. These last from about 400 million to 20 billion years. Interestingly enough, the life expectancy of our star is about 10 billion years. We're about halfway through that life expectancy. As a star ages, it gets more compact. The hydrogen is fusing to helium. We don't think of helium as very dense, but it's 4 times as dense as hydrogen. So the star is getting more compact, it's getting hotter. All stars heat up as they age, including our sun. That means it was a lot cooler way back in the beginning, and it's going to get hotter in the future. We can predict the end of the world. I'll tell you, it'll happen 3 times. What do I mean by that? Okay. In 500 million years, the sun will have heated up so much that life on Earth will be impossible for multicellular creatures, such as us. End of the world. In 1 billion years, it'll get so hot that the bacteria can't live here. end of the world. In 5 billion years, the sun will go into its final phase called the red giant. It'll expand out to the orbit of Earth, swallow it up, truly the end of the Earth. Well, let's get into the giant stars. 3 to 8 solar masses. They have a lifetime of 100 to 400 million years. And the supergiants, from 8 up to the theoretical maximum size a star can get is about 100 solar masses. A star that light only lives 1 million years. 1 million years sounds like a lot, but it's going to be only 1/10,000th the life of our sun. So what happens in these giant stars is a little bit different than it does in our smaller ones. For instance, we know that the hydrogen fuses to helium, but as it gets more compact, the helium starts fusing to make carbon, and the carbon to neon, and the neon fuses to oxygen, and then silicon, and then iron. This is the end. Iron is the most stable element. That means there's no energy to be gained by further fusion. When that happens, gravity wins. There is no more fusion. As you see in the picture on the right, all those arrows are pointing in. The star implodes, happens in some tiny fraction of a second. The energy created in that collapse is so great that it actually blows the outer layers off, as you see in the picture on the left. And that's known as a supernova. Death of a giant star. This is the remnant of a supernova. It's called the Crab Nebula. Now, this energy in the supernova is so great when all those things are blown off and there's so much energy and so many particles running around that you get fusion beyond that. It creates all the elements in the periodic table. That's the legacy I was talking about. So, petunias, pandas, people, planets, we are all stardust. By the way, the elements circled in red there don't exist on Earth because they're radioactive and their half-lives are such that they all decayed away before now. But we have made those elements in nuclear reactors, and they undoubtedly existed early on. And the giant stars, when the actual core collapses, gravity is so great, the protons and the neutrons are forced together. They become, the protons and the electrons are forced together. They become neutrons. That is so dense that a sugar cube sized hunk of neutron matter, size of a sugar cube, would weigh as much as Mount Everest. They were first predicted in 1939 and discovered in 1967 by a graduate student by the name of Jocelyn Bell. And she found this, she was running the night shift all alone on a giant radio telescope. And she got this beep, 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 beep. And her first thought was, oh my gosh, I have just detected the first extraterrestrial beings. The world has changed, and I'm the only one that knows it. Well, she was wrong, but. And the supergiants are so big that they form black holes. Even the light can't get out. Somebody suggested black holes in 1784, but the theory wouldn't really start getting developed until the 1915 with Einstein, and it was further worked on right up until 1960. The first ones weren't detected until 1971, and they were first photographed in this year. It took 8 large telescopes, radio telescopes, working in tandem, spread out over the entire face of the Earth, and a month dedicated on a supercomputer to put all the data together. And that's the picture which blew the astronomers away because Looked exactly what they expected it to. Get a little bit into quasars. That stands for quasi-stellar objects. They were first detected in the 1950s. They were far away and so terribly energetic that people started worrying if one were to happen in our galaxy, it would probably wipe out all life in the galaxy, including us. By the 1980s, we knew what they were. These are supermassive black holes. And when the galaxy is young, all the material around it, they call it feeding, but it's being sucked in by the radiation. And as it spins faster and faster, it gets hotter and hotter, and it outshines the whole galaxy, all the other stars. But as soon as all that material is gone, the quasar turns into a quiescent black hole. So we don't have too much to worry about. We have other things to worry about. When the universe was about 4 billion years old, the quasars began diminishing. They peaked at that point, and they've been diminishing ever since. So they're not likely to happen in the future. So the lives of the stars are complicated, as I'm sure Mr. Tyson found out if he read that book on Hollywood. But the stars we're talking about are complicated too, and much more so than I've told you now. But that's enough to get a general idea. So we were talking about the first billion years when all this, when the small galaxies formed. By 3 billion years, the small galaxies were merging into larger galaxies, and the supermassive black holes were forming. By the way, supermassive black holes can weigh millions and even billions of solar masses. And turns out there's one in almost every galaxy, including our own. The center of our Milky Way, we have a supermassive black hole that's some hundreds of millions of solar masses. And we move up to about 8 billion years. What's happening now is stars are forming, the universe is growing colder, and at 8 billion years, our solar system starts to form. And we're going to use a different dating point now, and I shouldn't call it our solar system, it's the solar system, because there's only one solar system. It's named after our star, Sol. So, I'm going to go through, these are my thoughts, and I probably should leave this out, but I'm fascinated by it, so I'm going to go on. The only way that was able to explain why the universe, that the bright boys have ever found to explain why the universe wasn't evenly spread, so evenly spread that masses wouldn't form to give us galaxies and stars, etc., was by saying that the universe expanded faster than the speed of light for a very short period. We're talking fractions of a second. And that made it work out. And most all of the theoretical astronomers accept that now. But it appears to me that, well, it doesn't appear to me, it is a fact that if we look in any given direction long enough with a big enough telescope, we will see galaxies way out there, 12, 13 billion light years, receding from us at 9/10 the speed of light. That way. So compared to each other, they're exceeding the speed of light. So I don't see any reason why we have to say the universe quit expanding at the speed of light after 1 second, or pardon me, after the very beginning. Appears to me it still is. So, one of the big questions was, what's going to ultimately happen? We got the Big Bang, everything's flying apart, gravity's slowing it down. Will it continue to fly apart forever, or will gravity finally win and pull it back together in what's called the Big Crunch? There were two groups working on this expansion to figure this out, and both groups came up with an answer within a month of each other in 1998, and they found out, to everybody's amazement and shock, that the expansion is increasing. My view of that is because we are The galaxies are all embedded in this expanding universe, so they're being carried out with it. So we are not necessarily expanding faster than the speed of light the galaxy is, and we're being carried along with it. But we also know that everything is subject to gravity and outside forces. If it wasn't the case, we wouldn't be able to guide our solar probe or our probes. So, taking the universe there, you think, then that's the case. Everything must be falling toward the center. And it turns out that in 1988, a group found out that our whole galactic system was accelerating toward something they called the Great Attractor. They didn't know what it was. I maintain that the Great Attractor is the center of the universe, and we are falling toward it. Of course, as we get further apart, the effect of gravity would be less, and indeed that 1998 study found out that the expansion is slowing, and it continued to slow, overtaking the expansion of the universe for about 7 billion years, and then it began to accelerate. So it really takes a little longer to think about that, but I don't have time, so we'll get back on track here. So this is a picture taken by Hubble. It's called the Pillars of Creation. It's beautiful. It's 7,000 light years away, and that is mostly dust and gases and particles, and it's the birthplace of new stellar systems, new stars, and that's probably where our, in a place like that is where our solar system started 4.6 billion years ago. The main epochs of the solar system are gravitational collapse. The gravity pulls it together. When it gets, the angular momentum starts it spinning, so it forms into a disk. When it gets compact enough, fusion starts. The star is born. Then the star will heat up all the ices in the inside, and the solar wind carries them out, clears out all the volatiles. The debris then starts consolidating into tiny particles. What happens is, first, there's electrostatic cohesion, and the little particles pull together. And then, as they bump into each other, they will adhere just to their natural adhesion. Eventually, you get large enough particles that they bounce into each other, they'll shatter each other, but some of them will hit gently and stick. And eventually, you get something large enough that it won't be shattered anymore. These are become planets. And the gases, as we said, are driven out, so they're going to collect in the gas giants. The first one, this being Jupiter, the first of the gas giants. We'll concern ourselves with Earth and the other rocky planets. They are at this point molten due to all the energy that's been put into them from all these pieces falling on them. But they start to cool from the outside, form a shell. And in Earth's case, another planet, which has been called Theia, ran into the Earth at a very, very early stage of formation. Maybe you can see the picture here. This Mars-sized planet in the top left picture is coming in, and in the second picture it strikes. It blew debris out, and it tilted the axis of the Earth, and eventually the debris consolidated into our moon. We have the largest moon by far compared to the size of the planet, and this is the reason. And the moon gets further away due to the tidal effects lessening the energy in the moon. Another interesting fact here is that the Earth is tilted because of this. That causes our seasons. If it weren't for that, we would have no seasons. Wouldn't be easy to measure the Earth, the year. Probably only astronomers would know that we had a year, and then, I don't know, we'd measure time in, I don't know, kilodays and megadays maybe, I don't know. This hasn't been known since only about 74, and they discovered it from the rocks that the astronauts brought back from the moon. And then when they started looking for ways to test this theory, the astronomers have found a lot of other evidence. So it's pretty well accepted that this planet hit Earth, and that's what caused our moon. Of course, all the volatiles, including water, had been driven away. So it came flying in comets and asteroids from the outer solar system. And it is thought that by 4.4 billion years ago, we had a water world. Some people even think that life came into existence by 4.3 billion years. I'm not quite sure how I found the people who say they have evidence, but I can't find any place where they say what the evidence was. So I just put it in here because it's interesting, because it's not in any way proved. But one of the things that would make it hard to prove is there's something called the heavy late bombardment. Something happened in the outer planets. They shifted around a little bit from 4.1 to 3.8 billion years ago, and it disrupted all the smaller comets and asteroids out there, and they came raining down and pulverized the surface of Mars, Earth, the Moon, Venus, Mercury. And once again, the Earth was sterilized, and the volatiles were driven away, and we start all over again, collecting water and the other gaseous elements. And since we're talking about Earth, we should talk about plate tectonics, which is the most important geological feature on Earth. Very simply put, the mantle is fluid, molten. There are convection currents. As you can see in the picture, there's convection currents through friction are pulling the plates apart. So where they're ripping apart there, the molten material goes up to the surface and cools. And on the edges where two plates meet, one of them dives under the other and remelts. And this was not recognized until 1968. The first guy who theorized it was a crackpot by the name of Alfred Wegener. He's a visionary now. Most visionaries started as crackpots, but I have to point out that for every crackpot that becomes a visionary, there are 1,000 crackpots that never make it. When I was in undergraduate, in an attempt to become well-rounded, I took a whole lot of Introduction 2 courses. The most fascinating one was Geology 101. And then they told us, look at how nicely South America would fit into Africa. Now, if you take the continental edge instead of the coastline, it fits even better. Isn't that interesting? Well, moving right along. I think it's interesting that the most important process in geology wasn't discovered until 1968. And there are the plates. The red lines show the plates as they were found in 1968. Well, took a little while after that. The reason that we know this is true is because of the paleomagnetism. You see, as the new material is forced to the surface, the magnetic particles align with the poles. And so it's going north to south, and the stuff cools, so they're locked in place. But as it spreads, ever so often the poles shift north to south, and the strip that's magnetizing shifts also. And in '68, the data was released that showed just that. Strips of ocean floor, starting from the middle, alternately magnetized north to south. So this was the place where continental drift was finally accepted, although the evidence on land had been building for a long time before that. There's a little better picture of it. You can see on the left there, you can see the seafloor spreading. Say that 10 times fast. And it spreads out. The new seafloor is being built there. The second one over there is not on a great ridge. That's just a little compact area. It's called a hotspot. There's a hotspot under Hawaii. It's a series of volcanoes. And as the seafloor moves, we get a new island. We have an active one now. We have a whole string of other islands which were volcanoes which are no longer active. We have a new one forming which will surface in about 10, 20,000 years. Then we go a little further to the right and you can see where the seafloor dives under the continent. It starts melting. It starts volcanoes along the edge. That's Mount St. Helens and all our volcanoes. Matter of fact, they go around the whole Pacific. It's called the Ring of Fire. There's a ring of volcanoes around the whole Pacific. Those islands I was talking about, they get scraped off and plastered onto the surface or onto the edge of the continent. That's how Washington, Oregon, and California were formed. And, of course, a whole bunch of other places beyond. So, plate tectonics is very important now. It's necessary for life because it recycles water and carbon dioxide, which otherwise would end up subsurface. These things come up through volcanic vents, hot springs, boiling mud pots, all the thermal features. They're resurfacing all that. The molten core is also very important to us because it's what forms our magnetic shield. That's what makes the Earth magnetic. That magnetic field is deflecting the solar wind around our planet. If it didn't, it would, in short order, abrade the atmosphere away. That's what happened to Mars. So, remember this. This is important. Nothing in geology makes any sense without plate tectonics. Did I say something like that a little while ago? Yeah. Anyway. So, the son-in-law will now entertain your questions. By the way, I told you that that's a good question means that I don't know. There's another definition. Sometimes when I say that's a good question, that means I do know the answer and I really want to tell you.
Can I? Me? Okay, Irene, listen, okay, so all the water on Earth came from comets.
That's the current theory.
But where did the water make the comet? I mean, what made the water that came from that made the comet in the first place?
That came from the deaths of the stars, what we just talked about, where all the elements were made, including oxygen, and the oxygen combined with the hydrogen. So, yeah, it's stardust too.
Hi, Ken, Bob. Great presentation. Really enjoyed it. The question you didn't get quite to it, but it had to do with cosmic expansion accelerating, this recent discovery, 1998. Have you come across any explanation? Because in classical physics, for acceleration to occur, there must be energy going into the system. And I have not seen any discussion at all explaining where this energy is coming from that would be causing an acceleration.
Nor have I.
Okay.
But my theory is that it's embedded in the expanding universe, and where the energy comes from to keep the universe expanding.
Hi, Ken. This is Cassia. I have a similar question, and you may have answered this, and I may have missed it, which is, it seems that all of this is dependent upon gravity. Where does gravity come from?
Gravity is a bit of a mystery because of all the forces. It is by far the weakest. I don't know. Nobody knows really where gravity comes from. It's like the elementary particles, you know. At the very beginning, at the start of the Big Bang, all these things were together, and it separated out into the elementary particles and the forces. And why there are forces and why there are elementary particles, we're pretty fuzzy on the very first instant, but we got a pretty good handle on everything that happened after that. Like I said, those people recently discovered what they thought was a mini Big Bang. Will be really interesting to see what comes of that in a year or two. I'll be watching the periodicals.
Yeah, hi Ken, this is David. I worked on board an oceanographic ship in 1969 where they were measuring the magnetic floor of the ocean off of Washington, and they found out the areas where the magnetism flipped. And it does that periodically, and that really puzzled me.
Well, now you know the reason. I understand that this was the military in their submarine program knew this was happening for some time, and it was a military secret. And when it was finally reported, then a bunch of geologists said, aha!
Ken, this is Ken.
Hi, Ken.
It seems to me that some distant point in the future, astronomers will look out from Earth and not see a darn thing.
That is true. It probably won't be on Earth, but at some point, all the other galaxies will recede beyond our seeing. And our galactic group is coming together. So they will form one humongous galaxy. And astronomers at this far different way in time in the future will be hard-pressed to figure out what began, because then it will be what it was thought before Hubble. There'll be one island universe, and they won't have all these other things for clues. So you're right. They'll go over the horizon. They'll be traveling so fast that the light will never reach us.
Ken, this is Don. I have a question and I know the answer. It's time for a break. Okay, let's take 10 minutes.
Okay. We're getting on now to the origin of life, and like the origin of the universe, we're a little fuzzy on the first step. But everyone agrees that it started with a self-replicating molecule, which was probably RNA, ribonucleic acid. Ribonucleic acid is composed of amino acids, simple sugars, and phosphate. It turns out there's a very famous experiment done by Urey and Miller in '53, in which they took the gases that they thought were in the atmosphere and water and some simple salts and sealed them in a flask, sterilized it, and then they spent a couple of weeks shining ultraviolet light on it and zapping it with electricity once in a while, and they formed a dark residue, and when they analyzed it, it was amino acids. It turns out they're pretty easy to make. The scientists have discovered amino acids, and they write down here, but sugars in space, so they might have been made on Earth, the building blocks of life, or they might have come in from outer space. But they formed these RNA molecules, which are capable of replicating themselves. It's the first life, if you will, and they're capable of evolving. All that means is they don't make perfect copies. And eventually, they got one that could build a copy on itself, and it's called DNA, or deoxyribonucleic acid, and I'm going to be in trouble here, I can see. Interesting story, the guys that discovered DNA were Crick and Watson. They were Englishmen in '53, and the night they figured that out, they said, let's go down to the pub and celebrate. And they bought around and they said, we know the secret of life. And the guy said, yeah, sure. How about another round? So, the replicating molecules are floating around in the ocean and are getting all kinds. And what they think happened, the bright boys, we're talking the biologists now instead of the astronomers, think that proteins, they started forming protein shells around themselves because they got trapped in a little bubble in the clay, or some folks think it might have been in a puddle that dried up and then re-wet itself again. But anyway, they formed protein shells around themselves and became the very first cells. And then these cells eventually started incorporating other of these floating molecules and even other cells. And sometimes they just absorbed them, and sometimes they incorporated them. And so all these little entities are living inside the cell. You can consider the cell an interdependent community as much as you can a living organism, because inside that wall, there are a whole bunch of little things living together. I'm going to have to read this to you because the computer did this to me. So these are black smokers, or pardon me, these are hydrothermal vents at the bottom of the ocean, and they shouldn't have been a surprise because after people accepted continental drift and they knew this was coming up, they should have known this, but they were a surprise. In '77, they found the first one of these, and it came as a great shock, and it came as even greater shock when they discovered life around them. The bottom of the ocean was supposed to be lifeless. It was cold, it was dark, there was no way for them to get energy, and yet around all these hydrothermal vents, there was life. Then in 5 years, they discovered black smokers. They're essentially hydrothermal vents, except they are bringing up lots of dissolved minerals. And when they hit the cold water, they start smoking or condensing out, and they build these tubes that can grow up to 40 or 50 feet from the floor of the ocean. And this is thought to be where life originated. If you think about it, what did the first life eat? There were no plants, there were no animals, but the life still exists there. There are clams, crabs, in the complete absence of light, and they're now powered. The bottom of the food chain are cyanobacteria, and those bacteria are chemosynthesizing, instead of photosynthesizing, hydrogen sulfide. That's where they get their energy. So these communities down there are not dependent on the sun or anything else. They're dependent on minerals, mostly hydrogen sulfide, coming up from the center of the earth. The first communities, the first life that we found fossil for sure, dates back 3.5 billion years, and they were stromatolites. They still exist. These are in Shark Bay, Australia. They're nothing more than little colonies of cyanobacteria, which kind of live together, and they trap grit and little pieces of sand, and so they build these rocks slowly over a long period of time. But there's very good evidence that life goes back to at least 3.8 billion years. And this is an auspicious date because if you remember, 3.8 billion years ago was when the great late heavy bombardment ended. That means that life began almost as soon as it was possible for it to exist. You can, if you wanted to bet, you could say that makes life fairly likely to form on an Earth-like planet. As life got more developed, the cells got more developed, some of them started to photosynthesize, and they're giving off oxygen. This is a picture of the blue-green algae, which was not the first thing it did, but is a photosynthesizer, and it's called the architect of the world because it makes oxygen. We had something called the Great Oxygen Event. It started 2.4 billion years ago. These oxygenators started making oxygen. It's a waste product. It's actually toxic to most life then. But it didn't build up because the oceans are full of dissolved iron. And for 50 million years, all this oxygen is oxidizing the iron. That is where our great iron deposits came from, like the one in Minnesota and another one in West Australia. But when the oxygen was all precipitated out, when the iron was all precipitated out by the oxygen starts building up in the atmosphere. And you can see on the graph there, 2.4 billion years ago, it starts building up. This created a great crisis for life because, as I said, oxygen is toxic. These guys are suffocating in their own waste product. This was the first mass extinction. Now, I'm going to take you through mass extinctions. And the first one was the Great Oxygen Crisis, 2.4 billion years ago. 99+% of all organisms living at that time went extinct. Oxygen poisoning. Some of them learned to tolerate it. They are our ancestors. Some of them hid where there isn't any oxygen, and they're still there today. So let's go back here and look. Another thing, notice the red spot there on the high spot. That's the place where the oxygen was the most concentrated ever, and it was during the Carboniferous period, and we'll get to that a little later. Another thing the oxygen did is it started building up, is it oxidized all the methane in the atmosphere. Oxidized it to carbon dioxide. Now we all know that carbon dioxide is a greenhouse gas. That was keeping the earth warm. You have to remember the sun was cooler back in those days. But methane is much stronger. I think it's, if I remember correctly, 22 times stronger greenhouse gas than carbon dioxide. So the earth started cooling down because of this, and something happened called the snowball Earth. There were a series of these events where the entire Earth was glaciated. The last one ended 640 million years ago. It wasn't known that this had actually happened until the 1990s. That was when the geologists started discovering evidence of glaciation near the equator. The effect on life, well, the photosynthesizing plants would have been restricted to very little places like you see there, the little strips of blue there. But the creatures that lived at the bottom, like tube worms and gastropods, they went happily on as though nothing had ever happened. These are some other things that still live down there. There are certain fish, there are octopuses, There are all kinds of crabs. There are hundreds, literally, of species that live down there, completely independent of the surface, living on hydrogen sulfide. The bacteria are synthesize that, and they are the first step in the food chain. I'm going to take a quick detour to the ocean moons. This doesn't have anything to do with us, but I think it's fascinating. This is Europa. It's a moon of Jupiter. It's about the size of Mars, and it has an ice crust that's 10 kilometers thick, and under that an ocean that's 100 kilometers deep. It contains twice as much water as all of the oceans of Earth. And that water is kept unfrozen, thawed, by energy that comes from the planet going around, the tidal effects, actually. The tidal effects of the heavy planet of Jupiter are putting enough energy into that to keep that going. There's the moon Enceladus, moon of Saturn. Here you can see actual vents, geysers. These are water geysers. This is taken by one of our spacecraft, which actually flew through them. It detected certain salts, nitrogen, carbon dioxide, hydrocarbons. This is the stuff of life. The reason I brought this up is it's quite possible that life exists under those ice shells, and there are lots of boys working for NASA now, boys and girls, working for NASA now. By the way, one of those is going to be my granddaughter. She's an astrophysicist student right now. They are working on probes which can go there and look for life. There's Ganymede is another moon that's thought to have an ocean underneath it. Okay, well, back to back to Earth. Okay. We're now down to 2 billion years ago, and the first true multicellular creatures have evolved. This is pictures of what they looked like. See those palm frond things? These are all soft-bodied plants, by the way, so they didn't fossilize very well. But those palm frond looking things, they're pretty mysterious. We don't know whether they were plants or animals. But they were existing, and they're jellyfish-looking things and seaweed-looking stuff. And then something really suspicious happened 540 million years ago. It's called the Cambrian explosion. That wasn't an explosion per se. They call it that because life suddenly exploded on the scene. And all these hard-bodied creatures showed up in a very short period of time geologically with a fantastic array of different life. Remember I told you about Geology 101? They told us, well, Cambrian explosion happened, there was no life before this, and all of a sudden, all these creatures came into being. How did this happen? Well, we now know that there were 3 billion plus years of history beyond that we didn't know when I took Geology 101. Just go through some of the creatures that were existing in the Cambrian period. There are the graptolites. They look kind of like starfish, but they must have been entirely different. There's this guy, which Wiwaxia, which was an ancestor of snail, and those knives sticking out of the top must have made it really good protection, hard to eat. Trilobites were probably the most successful creature ever to exist on the earth. They were around for hundreds of millions of years, hundreds of species. They were by far the most common, and you see trilobite fossils everywhere. This is probably the weirdest. It's called hallucigenia. There's no coincidence. That sounds like hallucination. The first picture I saw of this thing, it was the other way around. It showed it walking on those pointy spikes. I thought, boy, that doesn't look logical. And it had strange-looking tubes sticking out of its back. somebody did a little more analysis of the fossils and found out the tubes were actually in pairs, so they turned it over and decided those were the legs. But the bulb at one end, that's the head, well, some folks now are suspecting that in the process of fossilization, it got crushed and squeezed its innards out through the anus, and the head's at the other end. So we don't know exactly. This is my particular favorite of the Cretaceous. It's called Anomalocaris. Now, once again, when I took Geology 101, they showed us a fossil of the mouth parts, which you see in the lower left there, and they said, nobody knows what this is. Maybe if you become a geologist, you can figure out what kind of an animal that was. Well, now we know it's the mouth part of this thing, which, by the way, is an ancestor of the shrimp. They were about 1 meter long, and they were the apex predator of that time. And we have found a bunch of trilobite fossils with bites taken out of them. This guy would swim along. He had these 2 arms out front that would scoop things into the mouth that was underneath. By the way, the first Burgess shales, the first Cambrian creatures were found in the Burgess Shale, which is in the Canadian Rockies. It was discovered in 1909, coincidentally by a guy named Burgess. What are the chances? We since then have found other Cambrian fossils in China and Australia. Now, we're not through with the fossils yet of the Burgess Shale. Here's an article, Science News, this year, a brand new species that was found in the Burgess Shale. So 110 years, and they're still finding new creatures in there. We talked about the mass extinction. The second one was 440 million years ago, ended the Cretaceous. 86% of all species died. This was thought to be caused by a short, severe ice age. The Appalachian Mountains were growing at that time. They were at least as high as the Himalayas. Some people think higher. A lot of weathering, erosion was going on. This sucked a lot of carbon dioxide out of the air as it reacted with the rocks. So the greenhouse effect went way down. We had a short, severe ice age. 86% of the creatures died. What made it through? Well, one of them were the worms. The worms were actually Precambrian, and they survived. Here's a fossil of one. And the worms are important because they developed notochords. And the notochords developed into chordates. Those are backbone creatures. Take a good look at that creature there. She's your million-time great-grandmother. By 500 million years ago, some of the worms had evolved into fish. Now the fish had a long ways to go. You notice no fins, no jaws, but they were the first fish. Now remember this is important. Nothing in biology makes any sense without evolution. Did I say that? Anyway. By 485 million years ago, the first creatures, plants actually, invaded the land. They were moss and liverworts, simple plants, but first hold. Followed in 5 million years by the insects. The insects quickly developed into a bewildering variety of species, and they got very large. In the Carboniferous period, you remember we talked about the oxygen level went up because the world at this time was warm and swampy and covered with ferns and horsetails and the like, generating lots of oxygen. And this allowed the insects to grow large. This is the size of a dragonfly seen there with the person. This is a model, so you can get an idea. and this is due to the high oxygen levels. Now, there is a limit to how big insects can get, and it's well before this one. That's because they don't have lungs. They have little holes called spira. I can't remember, and I can't read it there. Anyway, they have these little holes in their body with little tubes that go in, and they have to rely on the air by osmosis. So that limits the size they can get. But during that high oxygen period, we got creatures like this. That insect was about 8-9 feet long. I saw a picture, which I decided not to put in there, of it reared up on its back 40 or 50 legs, towering over some guy who's cringing like this. And the insects had the surface of the world to themselves for 100 million years. Quite a long run. Meanwhile, in the ocean, the fish had finally developed jaws by 450 million years ago. And by 400 million years ago, some fish had developed lungs. Their bladders had evolved into lungs. And this allowed them to crawl out. It says here they're wandering, but most likely they were desperately trying to escape a drying pond. Of course, that's what the biologists say. Gary Larson had a different explanation for why they got out of the water. In another 5 million years, some of them had evolved into amphibians. That meant they could live on the surface, but they couldn't get very far from water because their skins had to be kept wet, and they had to go to the water to lay their eggs. So they were still tied to the aquatic creatures, but could live on the land. And the next mass extinction, 375 million years ago, 75% of all species died. This was because they think the land plants were stirring up sediment, just like the the mountains did earlier, and this created algae blooms, which used up all the oxygen and killed all the bottom dwellers, which, by the way, we are doing right now with fertilizers. We're putting too much on, it's washing off. We have huge Z zones at the mouths of most major rivers, which drain agricultural areas. By 300 million years ago, the climate had changed again. It became hotter and drier. The amphibians of the time went in a steep decline because it's hotter and drier, hard on amphibians. But they are still around, although they've been having a string of bad luck lately, if you've been reading about that. And there are many species of frogs are going extinct now. But some of them are still around, and some of the lungfish are still with us. They live in Africa and Australia. But during this hot, dry period, as usually happens, some of the amphibians evolved into amphibians, I can't even read that. Arthrosaurs, thank you. And the arthrosaurs had two advantages over their predecessors. They had a better skin, which could protect them, didn't have to be kept wet, and they had hard-shelled eggs, which didn't have to be laid in the water. So they were freed from the water, which was getting a little rarer in those days. And then the arthrosaurs quickly started evolving because they had all these open niches. Some of them became reptiles, and some of them became therapsids. And the therapsids are kind of important to us because they went into a lot of different species. Some of them were very large, and some of them were wonderfully ugly, and some of them were both large and ugly. And they are the ancestors of the mammals. And here we see a saber-tooth whatever attacking a, I don't know what that looks like. But there was some of those in existence at one time. And the next mass extinction, 252 million years ago. Pretty sure that this one was caused by very large lava flows in what is now Siberia. And this pushed out tremendous amounts of CO2. This caused the bacteria to, the methanic bacteria to start producing methane. The temperature went way up. The oceans became stagnant and then started developing hydrogen sulfide. So this was a really bad time. 96% of all species went extinct. It's called the Great Dying. Going to take a little detour here on mass extinctions. Catastrophes, mass extinction can and have happened. Most of them have been due to climate change. Of course, couldn't happen now, could it? Can it? I'm going to go into a short rant now about Egyptian swimmers. That is, those in denial. This is actually an Egyptian farmer on the Nile. His name is Mahmoud. I talked to this guy a month ago. One of the people in our party asked him, have you noticed any change in the weather in the last few years? And this simple Egyptian farmer said, oh yes, global climate change is a real problem. He said, we used to have 4 seasons, now we have 2. The summers are longer and hotter. The crop yields are down. This is a picture from the Salem newspaper, an article, September of this year. The headline, Climate Panel Sees Dire Future. In November of this year, 1,100 scientists declared a climate emergency. Not too long ago, I read about a city, Jacobabad. That's a city of 1 million in Pakistan, where the summers are now so hot that healthy adults can barely survive, let alone work and make a living. The power failed, the air conditioning went off, and they lost all the infants in the hospital. Same thing's happening to the older folks. These million people are soon going to have to go someplace else. Consider Bangladesh, population of 130 million, most of which is just 1 or 2 meters above sea level. When the sea level rises a little bit, 100 million people are going to have to move. Think of the dislocations we're having now trying to deal with a few 100,000. What's going to happen when we have hundreds of millions? Here's 2 respected magazines, Scientific American and Time, who the second half of this year dedicated a whole issue to climate change. They're not arguing that it's happening. That's a foregone conclusion. They are talking about what the effects are going to be and how we might avoid it if we work on it. This is our second greatest challenge, the first being avoiding an all-out nuclear war. Okay, that says the reasons for denying climate change. And that next one says ignorance. Of course, in the face of all this evidence, you have to work at being ignorant. You have to really decide that I'm going to ignore all this stuff. I call this ignorance to the point of stupidity. I have tried to be diplomatic and I've given up on it. There are some people that aren't stupid who deny climate change. They're usually dealing with greed. These are people who either make a lot of money from fossil fuels or who get the money from the fossil fuel folks. And they are changing, they are selling their future for a short-term profit. This is greed to the point of criminality. These people will tell you, hey, scientists lie to get grants. Okay, I once considered myself a scientist, and I have to tell you, science is self-correcting. There are several mechanisms by which science is self-correcting. You tell me what the self-correction is for politicians. They'll also tell you that scientists don't know everything. Well, that's true. If they did, that would be the end of science, wouldn't it? But I will tell you what they've discovered when they hypothesized what's going to happen in climate change. Generally, in the cases where it's come to pass so far, the worst case scenarios have been optimistic. There are some tipping points beyond which we don't even know what these are going to be like, but what the effect is going to be. One of them is loss of the Arctic sea ice, because the ice is white, it reflects the light back, the oceans are dark, they absorb it. The Arctic is warming faster than any other part of the planet. There's thawing of the tundra. There are millennia of plants frozen into that tundra. And when they thaw out, they start decaying. There's a picture on the right, it's not a very good one, but what you see is a flame there. That's a place in Alaska where the methane is actually coming off enough to light and cause that fire. And then there's one that nobody really understands very well, but there's tremendous amounts of methane tied up in the bottom of the ocean and methane hydrates. It's kept there by pressure and cold temperatures. And what happens when the ocean's warm? Nobody knows. Nobody knows how much it would take. But the Aral Sea in Siberia is already giving off methane. So, is this really a problem? My answer is, yeah, that's really a problem. I think it's the second biggest problem we face, as I already said. And people will say, yeah, but is it capable of destroying our civilization? Well, damn right. So, what can I do? What can you do? Well, you can reduce your carbon footprint. This will help a little. I won't get into how you can do it. That's for another time. You can encourage others to do the same. Would you please reduce your carbon footprint? And we can vote for enlightened leaders. Enlightened leaders would be those that aren't stupid or greedy. And I'm not being partisan here. I saw a commercial once. Newt Gingrich, Nancy Pelosi on the same podium agreeing that they don't agree on much, but they did agree that climate change was a problem, and it was a nonpartisan problem, and we needed to work on it, and this was 15 years ago, and this was Newt Gingrich and Nancy Pelosi. Where have we gone wrong? I don't know. Okay. You know, these were my notes. Now I can't read them. What does that say? Oh, yes, on to a happier subject. Okay, I will get us off of that. What made it through the Great Dying? Well, some small shrew-sized mammals, some small reptiles. There's a pattern here. The little creatures make it through better. I found that, then they start growing larger, and I found this picture, I had to put it in there. There was a species of crocodile that walked on two legs. Oh my goodness. I know you can't read this, but just look at all the blocks on the right. Those are geological periods. The arrow down at the bottom shows the Cambrian. Up at the top shows where we are modern. Each one of those geologic periods is delineated by the fossils that it contains. Before geologists had the sophisticated means of dating, they used the fossils in it. Now, the mass extinctions caused each of these new waves. Now, they weren't all mass extinctions. I'm just reporting the ones that are over 75%. There were many extinctions periods that were less than 75%. And each one of them caused the loss of some iconic species and then the evolution of others to fill the niche. This guy's name is Stephen Jay Gould, and he developed a theory called punctuated equilibrium. And that theory says merely that there are long periods of evolutionary equilibrium punctuated by periods of rapid evolution, meaning things go muck without much change, and the same creature's here for a long time. Something bad happens, a lot of creatures go extinct. The ones that are left rapidly evolve to fill those niches. So, going to talk about the next mass extinction. 201 million years ago, 80% of the creatures of the species died, and we don't know what caused this one, but it did set up the period, did set up for the dinosaurs to take over as the major species. And then began the arms race of the dinosaurs, just like it happened before. So they grew bigger, and they grew better armed, and they developed feathers, and they got fiercer, and so they got bigger, and so they got fiercer. By the way, T-Rexes did have feathers. And they got gargantuan, and then, kaboom. Along came an asteroid, and the end of the dinosaurs. This was the mass extinction of 65 million years ago, killed 76% of the species at that time, wiped out the dinosaurs, and led the way for the evolution of mammals. Now, how do we know this happened? This is Luis and Walter Alvarez. The younger one, Luis, on the right, I think I've got the names right. Anyway, he's a geologist who was studying in rocks in Italy, and he discovered that the Cretaceous rocks above had lots of fossils in them, including dinosaurs, and below was the Tertiary, where there were a lot less species and no dinosaurs, and in between was 1 inch of black silt. And he wondered, he thought if he could measure the time that was, he could find out how long it took for this mass extinction to take place. And as luck would have it, he had a father by the name of Walter who thought that his son had abandoned the real things, the real sciences, because he was a Nobel Prize winning physicist. So the son goes to the father and says, "Dad, how can we figure out what the time period was?" And Dad thought about it a little bit and came up with iridium. Iridium is an element that has very little love on the surface of the Earth, but there's quite a bit in outer space, and these little micrometeorites that are always hitting every day, they burn up, and there's iridium and everything else drifts down as dust. And he thought, if we assume that this has been constant over time, we can measure the amount of iridium in this layer, and we can tell how long it took. So the son got up a sample and sent it off to a nuclear activation lab, and the answer they got back was mind-blowing. There was so much iridium in it, it couldn't have been possible, but it had to be. They had it analyzed again and again. So then the conclusion was something from outer space, it came from outer space, caused this problem. And within a few years, they'd come up with the theory of the asteroid. And now we know that it really was an asteroid, and it struck in the Yucatan Peninsula of Mexico, and it caused huge earthquakes and tidal waves, and caused acid rain. It caused showers of meteorites, ejecta, which was red hot, which started forest fires and burned everything down. But probably the worst part was the blast effect winter. The explosion was so big, this thing was thought to be 10 kilometers in size. By the way, I'm going to put in a plug here for statistics and rounding. People said 10 kilometers. That means it's somewhere between 5 and 15 kilometers. And then people round that up and they say, oh, it was 6.2 miles. 6.23 if you want to get real close. So all this dust is in the atmosphere, stratosphere, and it cut out the sunlight for years. Photosynthesis shut down, the plants died, the herbivores died, the omnivores or predators died. It might be a coincidence, I don't know, but very shortly after that, a bunch of people sat down and said, how many nuclear bombs would it take to simulate that? They called it a nuclear winter, and they came up with a number, and it was way less than either we or the Soviets had in their arsenal. Now, it might be a coincidence, I don't know, but about 1 year after that, we began serious nuclear disarmament talks with the Soviets. Of course, the dinosaurs aren't all gone. Here's one I photographed in my backyard. But only the little ones made it. Here's one looks pretty fierce, doesn't he? He's 4 inches tall. This one is a stork. It really looks kind of prehistoric. But if you look at the fossil record, there was something called terror birds, lived in South America, that regained some of the stature of the dinosaurs. And here's a picture of one who's taken down an ancestral horse. So, with the dinosaurs gone, the little mammal-like rodents, which had been living under the feet of the dinosaurs, started evolving to fill all those niches. And they evolved into fleet species like this four-toed horse, and huge species like the mastodon, an armored one like this early woolly rhino. Of course, strange things like platypuses. By the way, I looked it up. They really are mammals. And of course, aquatic species like mammals, like whales, and even the aerial species. And some of them became primates, such as lemurs, opposable thumb. If you look close, you can see the opposable thumb there. And monkeys, and apes, and humans. Of course, evolution isn't particularly straightforward or neat. They split. Species split for whatever reason because they get isolated. Sometimes they come back together. It's thought that there's good evidence that our species, Homo, split from the chimpanzees and then came back together and then split again irrevocably. Anyway, meet some of the family. And some of these are all the groups of Homo that we know existed. There may be more. One of them, called Denisovian, was discovered just within the last decade or so. Most of these have gone extinct, but there's some, like Neanderthal. Well, they're not really extinct. We are they. All of us Europeans carry a little bit of Neanderthal genes. There's one called Denisovian that didn't go extinct. Most of the Asians carry some of their genes. Okay, personal epiphany, little detour. I had two epiphanies when I was 12 years old. One of them, I was working on a ranch in South Idaho on the Snake River. One day I was walking through the pasture and noticed a cow not doing cow stuff. You know, cows graze or they lay down and chew their cuds, and this cow was just standing there staring off at nothing I could see. So I walked over to her and she completely ignored me. She was just standing there, blank-eyed stare. great big tears rolling down her face. Her calf had been removed the day before, and it hit me right between the eyes. Oh my God, she's mourning. She loved that calf. She raised that calf because she loved it, not because of instinct. You could catch a lot of other things that we think are only human, like crows think. Maybe you've heard the famous case of crows who taught themselves to drop rocks in pitchers to bring the water level up. Chimps and other animals use tools. As I discovered, cows love. I maintain from that day on that we are different from those other species, not in kind, but in degree. They all do the things we do, maybe to a different degree. I maintain from there that we are not, as we have named ourselves, Homo sapiens, which means wise man. If we were wise, we would be living in peace, prosperity, security. We have the technology, we have the resources, we don't have the will. If we were wise, we would have controlled our population so we wouldn't be overrunning the planet. We wouldn't be despoiling the very environment that we depend upon. No, I don't think we're wise man. I say we're the clever ape. We're clever enough to make wonderful inventions, like the wheelbarrow and the computer, and terrible inventions like the sword and the A-bomb. Which brings us to the 7th mass extinction. Only 50% so far, but it's accelerating, and it's caused by us. A lot of this up to this point has been either outright killing of species for whatever desirable traits that we wanted to take, or eradication of their environment, but more and more it's coming to be climate change. So, here are some of the groups. By the way, there's a book called The 6th Extinction, and that's talking about the one I'm talking about. They didn't count the one at the Great Oxidation event. They started a little later than that. So if you want to read about this book, it's called The 6th Extinction. And the groups that are on in particular decline at this time are amphibians, the mammals. By the way, when I took Geology 101, they told us the mammals were in decline. And one of my classmates asked me, well, what do you think is going to replace mammals? I didn't have an idea. I didn't know at that time. I know now. It's humans. The first time one particular species has predominated instead of one whole group. Also in decline, insects. This is very worrisome because they're the bottom of the food chain. And it's just 10 years ago they've discovered there's mass reduction in the numbers and species of insects. And birds, who to a large extent depend on insects. And fish and bats. I know bats are mammals, but I felt like putting them in there. So, we're into this 7th extinction, and people might ask the question, will we make it through? And I say, probably, almost certainly. We are a very adaptable species. But not all of us. There are already tens of thousands of people dying every year due to climate change. On the left, the things that make headlines: storms, floods, wildfires. But there are lots of other things that are a little more insidious, like infectious diseases and famine and heat stroke. There was headlines a couple of years ago of, I don't remember the number now, but it was something over 10,000 people died in Europe in heat stroke when they had a particular bad time. And famines are coming up rapidly because of arid conditions and lack of growing conditions. And I'm afraid that those of us that do make it through will be living in a sadly depleted world. So I say, is there hope? There is yet hope, I maintain. There's always hope. Without hope, we have nothing. But if we are to be saved, won't be by our clever 8 brains, but by our greatest invention. Want to take a guess on what our greatest invention is? My opinion. Well, it isn't fire, and it isn't the wheel, and it isn't even tools. Now, I think our greatest invention is civilization / culture. They're kind of put together there. And if you think about it, civilization, culture, has already caused us to give up human sacrifice, institutionalized slavery. I know you can read about slavery, but it's individuals now. The institutions don't back it anymore. Torture, we backslide on that one a little. And the things that we've made significant progress on so far, inconsequential prejudices, race, religion, creed, gender, sexual preference, etc. Capital punishment, okay, we're still working on that one, but it's down. War, yeah, believe it or not, we've made progress on war. Despite the fact that that the 20th century was so bloody, it turned out to be the least number of casualties per capita of any record, any century in recorded history. Another thing I read that blew me away, but I can't come up with any reason it's not true, said an article that said that no 2 democracies have ever gone to war against each other. Now, I can come up with one case, but I can also argue my way out of it on a technicality. And the newest one, environmental preservation. Those last 2 are in red there. You probably can't read it. But those I view as the most important one, because all-out nuclear war and environmental degradation are the 2 things that could destroy our civilization. The rest of these, bad as they may be, are not going to do that. So, oh yeah, I promised I'd give you some answers at the very start of this, so here we go. Douglas Adams' answer to the question of life, the universe, and everything. Well, in his story, that was the question that people asked, and they built the great computer, the huge supercomputer, and they asked it this question, and the computer labored for 7.5 million years, and then it came up with an answer, and it said, but you won't like it. But they insisted on knowing, and the answer was 42. Now, Douglas Adams says that was a joke, but there have been a lot of nerds who sat up all night trying to find the meaning to 42. Stephen Hawking said, why does the universe go to the trouble of existing? And in this book, he gives an answer. It took the whole book to do it. Boiled down at something like, there's positive energy in the form of matter. The stars, the galaxies, everything. And there's negative energy in the black holes, and the 2 cancel each other out. I could interpret that to mean the universe doesn't exist. And you might not like that one either. And mine, the meaning of life is, I warn you, you might not like it. Life has no meaning. Life, as we know it, matter of fact, the universe and everything is the end result, so far end, of an unimaginably vast series of happenstances which could have gone any other way according to chaos theory. That means if you could rewind the universe and start it over at any point, it wouldn't turn out the same. So how could we say that the way we are now has meaning? However, life does have purpose. And the purpose of life is living. And that is either very inane or terribly profound. I leave it up to you to decide. And that says, are there any good questions? And good questions mean either those that I don't know the answer to, or those that I do know the answer to are happy to tell you.
Yeah, we went a little overtime, Ken. Thank you very much for the
You're welcome.
thought-provoking